Hello, my dears. Here we will study the steady state error for a system with disturbance. System with disturbance is similar to the system you can see in front of you here, where the system is having input and output with a feedback unity as you see here, similar to the previous system, except if the system is affected by external signal and the external signal affecting the system at the middle of it. What does it mean here? In our example, the example I'm putting here, you will find controller and the plant. Sometimes there is external signal affecting them, so we are going to put the external signal as you see here. So the external signal is called disturbance, and it's added to the signal coming from the controller. That's if we assume that the disturbance is affecting the output of the controller. The disturbance is affecting the output of the controller. So that's how we can express it. And you'll find that the disturbance is added to the signal coming from controller. If the system is having this format, how can we find the steady state error, or how can we analyze the steady state error for it? That's what we are going to see. Similar to what we have done in the previous systems, we want to find equation to calculate or to evaluate the steady state error if the system comes with disturbance. To derive the expression, we are going to consider ds as a disturbance. This is the disturbance, and this is the input. So we are assuming that the system is having two kinds of inputs. One is the main input, our input, and one is the disturbance. So how to calculate it, or how to evaluate that equation? We will calculate CS. CS is coming from two different locations or two different paths. It's going to be RS entering to G1 and then G2 and then to the output. It's not from RS, it starts from this location, from ES, and we will continue. So again, the first location or the first path, it's coming from ES, continue until the end. And the other one is coming from DS and continue till the end. So notice that DS will be going through the plant only, but ES is going through both of them, through the plant and the controller. So when we put the expression, it's going to be placed like this. CS is equal to E into G1 into G2, E into G1 into G2, plus D into G2, plus D into G2. That's how we can consider it. Let us now evaluate the parts, the parts of the equation. So if I want to calculate E, what is E? This E is equal to RS minus the output CS. That's by definition. So if I rearrange this equation to calculate CS, CS will be equal to, from this equation, it's equal to RS minus ES. Now let me substitute this equation into this equation, equation number 2 into equation number 1. We will find, and rearrange it of course, we will find that ES can be calculated as this part minus this part. As usual, this kind of result is giving me the error at specific point, which may not be the end, of the response. And we agreed on something, that to get the response, it's better to go to infinity, because at infinity only we can figure out the distance between the error and the input, and the output. That's why we will apply the final value theorem, where in the final value theorem we are going to apply the limit for s multiplied into the function. So we will apply it and we will get the error equal to this. So the steady state error at infinity equal to the limit of this part into RS minus the limit of this part into DS. In general, we can say that these two parts I mentioned just now, they are parts due to input, steady state error due to input, which we call it ER, and steady state error due to disturbance. So we put them here to be E of infinity equal to the effect of input plus the effect of disturbance. Why I'm saying plus? Because usually it's plus. Whether the sign is positive or negative, that's going to be decided by the a feedback, whether the feedback is negative or positive. So here he's showing the conclusion. He's saying that the error for the system with disturbance is going to be the total of the error due to input plus the error due to the disturbance. So here he split them. The error due to input, the error due to input is calculated from this equation, and the error due to disturbance calculated using this equation. That's how we can evaluate the steady state error. Let us look at this example. Find the steady state error component due to step disturbance for the system shown. Assume the system is stable. Of course, always we will assume the system is stable. If I apply the steady state error, that means the system is stable, because unstable system does not have a steady state error analysis. So we are going to assume a step disturbance. That means there is a step signal coming here. If it's 1 unit, that means 1 over S. 1 over S is applied to the disturbance as a disturbance. What will be the steady state error due to disturbance, as he said? So we are going to assume ds equal to 1 over S, and we will use the second formula, which calculated earlier. Ed of infinity means the error due to disturbance at infinity is equal to minus the limit as s approaching 0 for this part. We will substitute the transfer function G2, as you see here, and transfer function of G1 into G2, that's given here. It's going to multiply it into ds, simplify, you will find that the error will be minus 1 over 1000. That's the error due to disturbance. Before I go to the next point, if he asks for the error for disturbance and input, you can calculate them separately, or you can mix them in one equation. It's up to you. You can do it either way. I mean, calculate the error due to input, then the error due to disturbance, and add them, or you can calculate them using the long formula one shot. Let us come to other point here. In this other point, he said how to evaluate the steady state error for non-unity feedback system. Notice all my discussion earlier for the system with unity feedback. Unity feedback means this feedback is 1. There is no block, no transfer function. This time he's saying, what if there is a feedback? There is, non-unity feedback means there is a transfer function for the feedback. How to evaluate it? We will find a way to remove the feedback. Let us see how to do it in the next slide. So what to do here? We are going to remove the feedback. We are going to convert the system as unity feedback. How to do this? To convert the system as a unity feedback, we will get the system as you see. This is the system. I will depend on colors here to make you clear. This is the original system. And we will add a feedback of -1 and another feedback of a +1. That means something like equation. We add 1, we subtract 1. So we add 1, we subtract 1. That's how you can look at it. Okay, after that, we find that we can use the block diagram reduction here to simplify or to rearrange the blocks. See, these two are parallel, so we can join them together. So they are going to look like here, HS -1. And the unity feedback, we will keep it. We will not touch it. So the system will appear like this. This is the feed forward, and this is the feedback. And the unity feedback, which we are looking for it, will remain here, will be here. I think it's very logic and very clear that we will further simplify this one. We will simplify this one using the block diagram reduction theory. So if you look at it, you will find that it's feedback. It's feedback. If it's feedback, how am I going to evaluate it? It's going to be something like we are having block here, and inside the block we will find this equivalent, which will be G over 1 plus G into HS -1. That's what he found here. G, the feed forward, divided by 1 plus feed forward into feedback. This is the product of feed forward into feedback. So if you notice, the system now looks unity feedback. The system now is unity feedback. We can apply the theory we discussed earlier on the system right now, because now it's valid. As example here, saying for the system here, find the system type for the appropriate error constant and the steady state error for unit step input. Assume the input and output units are the same. What he means by assume they are the same, he means the signal here having the same format as this one. So if this is electrical, this is electrical. If this is mechanical, this is mechanical. That's what he means. So notice that the system is non-unity feedback. We need to convert it to unity feedback. If you can keep the formula in your mind, I mean this formula, you can directly go to this point. You can directly go to this shape, the unity feedback, and apply the theory. If you cannot catch the formula, you can, as I explained in the derivation, you can add -1 and add +1, and you can simplify the block as we did earlier. So now this is the system. So now if I want to calculate the error, we need to calculate the feed forward block, because we said it's a change now. It's a change. It becomes GE, which used the formula in the previous slide. So use the formula, substitute the values. Finally, GE equal to this value. Now I can realize the system type. Before that, I cannot realize the system type. Don't commit a mistake by deciding on a system type by looking at the transfer function of feed forward. It's not acceptable. To apply the theory of system type, you have to put the system in unity feedback. So after its unity feedback, check how many integrator you have in the feed forward. Like you put the transfer function in this format. How many integrator we have? There are no integrators there. That means the system is type 0. Now, in this case, we can calculate Kp. So Kp is the limit of GE, the limit of this function, as is approaching 0, of course. We will calculate Kp to find it's -4/5. Now, substitute it in this formula to calculate the error. So it's 1/1 plus Kp. So Kp is 4/5. Substitute, you will find that the error is equal to -4. That's how we can calculate the steady state error for the system if it's non-unity. So if it's non-unity, we'll convert it to unity, then we will apply the theories we discussed earlier. Time domain analysis of continuous linear system, or what is known as a transient analysis. Let us start by studying the poles and zeros and the system response. System response is to be evaluated as a result of force response and natural response, where the force response is what is given by the input of the system, and the natural response is the system by itself, means the transfer function of the system by itself. So if I want to calculate C of t, it's going to be obtained by solving differential equation, or we can calculate it by finding the Laplace inverse by using Laplace, as we have studied earlier in the Laplace inverse. Of course, it have been found at the beginning when we study it that finding it by Laplace inverse is going to be much easier. Let us here understand the meaning of poles and zeros of the transfer function. If we consider this transfer function or the response of the system, which can be found on the output of the system, we are going to find in it poles and zeros. What are poles and what are zeros? Let us start by poles. Poles are the values in the transfer function which will make the transfer function equal to infinity. Like what? If you consider the denominator, because if the denominator becomes 0, we are going to get the whole function equal to infinity. So if the value of s equal to -p1, for example, -p1, we are going to get -p1 plus p1 equal to 0, which makes all the denominator equal to 0, which make the transfer function equal to infinity. From there, we call all the value of p's, p1, p2, p3 in the denominator are going to be known as poles. So here in this transfer function, s equal to 0, if s equal to 0 or s equal to -p1, these are the poles. So the poles are 0, -p1, -p2, and so on. Similarly, for the zeros, which explained in the next slide, that zeros are the value of in the transfer function, which will convert the response to 0. Means what? Let us look at the numerator now. Any value makes the numerator equal to 0. Any value make the numerator equal to 0. It will make all the function equal to 0. What are these values? Like s equal to minus z1 or s equal to minus z2. For that we call z1 minus z1 and minus z2 as the zeros of the transfer function, as explained here. The zeros are at s equal to minus z1 or s equal to minus z2. That means minus z1 is 0, minus z2 is 0, and so on. To obtain now CT, to obtain the output, the response CT, you remember when we discussed the Laplace, we find that we will calculate CS first of all by multiplying the input into the transfer function. You will get CS, and then find the Laplace inverse of the CS. Is going to give us the response. Like you see here, to calculate CS, it's equal to RS into GS, which equal to 1 over S, because here as consider that the transfer function, the input is 1 over S, one step unit. 1 over S multiplied into S plus 2 over S plus 5. To solve this one, or to find the Laplace inverse, we will apply partial fraction expansion. To calculate A and B, we will find that A equal to 2 over 5 and B equal to 3 over 5. By the method we discussed earlier, substitute them back in the equation, you are going to get this response. So this is the output in time domain. This is the response in time domain, and that's the way to calculate it by Laplace inverse. He showed the system and the representation of the system on the S-plan by showing that the system will have the response, have zeros, poles. So it's having, if I consider this point, this is the input, 1 over S, this is 0, and this is pole. So if I show them on the S-plan, you will find the 0 or the input, which coming as a S in the denominator, comes on the origin of the S-plan, and the pole, which at the 0, which at minus 2, 0 at minus 2 on S-plan, we write it at minus 2, we put it in a form of circle. Usually we put it as a circle. So circle means 0. The representation of 0 is a small circle on the S-plan. How about the 5, which is the pole? The pole is going to be represented on the S-plan, which coming at the location of 5 on S-plan, 5 negative, of course, because the pole equal to minus 5. So if it's minus 5, we are going to put it in S-plan as a X. If we want to see them on the S-plan, now try to compare them, their location, with the response we found. The response found just now, CS equal to 2 over 5 over S plus 3 over 5 over S plus 5. Where when I convert it to a time domain, I find that this is 2 over 5 and this is a 3 over 5 exponential of minus 5t. This is considered as a force response. This is considered as the force response, which coming from the input, and this is natural response, which going to show us the exponential function. It shows us exponential function there.